The first invariant quantity that one comes across in special relativity is the invariant length that one usually denotes by ds. Now let's consider just a frame of reference in which we have one dimension of space and one dimension of time. Now it's not important if you put time here and space here or vice versa. In this lecture I will put x here, the dimension of space, and then here we have the dimension of time. Now if we take a look at a light ray in this frame of reference, the light ray is described by an equation of the kind x equals st. So we assume that at time t equals 0 the light ray passes through the origin. So since its speed is the speed of light c, the equation that describes the light ray is x equals ct. Now the speed of light c in this case can also be written as the derivative of the position with respect to time, dx over dt, right? And if we do some math here, and we can rewrite this equation like this. We square it, c squared, and then we multiply by dt squared minus dx squared for a light ray. This is equal to 0. So this is true for a light ray. Now for a generic object, this quantity here that we have on the left does not necessarily equal 0. But for example, if we take another frame of reference in which we label the variable of time as t prime, so we have dt prime squared multiplied by c squared, and then we subtract the dimension of length, dx prime in this case, squared, this is still equal to 0 for a light ray. So the equation of a light ray, and in particular, this is not, I mean, you can call this the equation of a light ray, quote-unquote equation of the light ray. And if you change coordinates, and we will see that this will impose, this will force us to choose the so-called Lorentz transformations to pass from one coordinate frame, from one coordinate system to the other. We will see that, I mean, this equation here still holds in the new frame of reference. So you can see that the form of the equation is exactly the same. And this has to do with the fact that the speed of light c it can still be calculated as dx prime over dt prime because the velocity of the light ray does not change if we change our reference system, a reference frame. Now, for a generic object, instead of having 0 here on the right, we have the so-called invariant length ds, but we have the square of it, so ds squared. And one can show that in the new frame, we have c squared dt prime squared minus dx prime squared, and which is still equal to ds squared. And why is this true? Well, let's try to describe it succinctly. So I will do it very shortly. There are some more details that you can investigate yourself if you are interested, but it's not too complicated to understand why in general we must have something like this. We have a quantity which is invariant. So for a light ray, this will be 0, and of course this will be 0 as well. But for a generic object, you can see that this object is invariant because we have ds squared on the right on both of these two equations. Now, since this object here is 0 for a light ray, we know that for a generic object, we have ds squared, and ds squared must be 0 for the light ray, and that's okay. But let's assume that now that we have two frames of reference, okay? So one frame, we call it k, with coordinates x and t, and then we have the other frame, k prime, with coordinates x prime and t prime. Now, the invariant length for k, we call it ds, and the invariant length for k prime, we call it ds prime. So I'm calling it invariant, quote-unquote invariant, but we have to show that this is actually invariant. Okay, so let's call it ds and ds prime, and we calculate them in the fashion that we have shown here. So ds squared would be equal to this. So it satisfies this equation, whereas ds prime satisfies this equation here, where instead of ds here you have ds prime. We have to show that ds prime is equal to ds. Now, under the conditions that the space is isotropic and homogeneous, we are going to show that ds is equal to ds prime. So what does it mean that the space is homogeneous? Well, the space being homogeneous means that ds is equal to some constant, actually let's say a function of something, and we are going to say what this function depends on. And then here we have ds prime, so ds is proportional to ds prime. Now we must have this kind of proportionality because when one is zero, the other one is zero as well, and they are infinitesimals of the same order. So this proportionality must hold. And in principle, this function can be a function of the variables of space and time, and also the velocity, the relative velocity between the two frames of reference, because we have a relative velocity. And now this is the point, the important part, because if the space is homogeneous, it means that this function cannot be a function of x and t, of space and time. It can only depend on the relative velocity of the two frames, and the relative velocity is in general a vector, right? So it has a magnitude v and also an angle alpha, which describes the orientation of the two frames of reference, so of one frame of reference with respect to the other. Now, if the space is isotropic, it means that there can be no dependence on the orientation, so this alpha cannot appear. So it means that this function will be a function only of the magnitude of the velocity between the two frames. So that's what we must have. ds is equal to f of v ds prime, right? But at the same time, we can also change the way we look at things. So we can say, okay, ds prime must also be a function of something, and then it is multiplied by ds, right? And if we change our perspective, the velocity vector will change the sign, minus the vector v, because if one frame, so we have one frame here, x and t, and then we have another frame, x prime and t prime, and we have a velocity v with which x prime t prime is moving with respect to x and t, right? But at the same time, we can also say that x and t is moving with a velocity minus v in the opposite direction. So this is just a change in our perspective. So since there can be no dependence on the orientation, but only on the magnitude, this must also be a function of v, f of v. It must be the same function f of v, right? And these two equations together imply that f of v squared must be equal to 1. And that's why you can understand that f of v should be equal to 1. Now, there are other ways to show this. This is not the only way, but it makes sense that under these conditions of the space being isotropic and homogeneous, this element, ds squared, remains invariant. So this is the first step. So we basically can say that c squared dt squared minus dx squared is equal to c squared dt prime squared minus dx prime squared. Now, at this point, we can also rewrite this equation in the following fashion by using the imaginary unit I. So I can square I c dt. If I square it, I will get a minus sign from the imaginary unit, so here I have to put a minus to rewrite the same thing here. Minus dx squared equal to minus I c dt prime squared minus dx prime squared. Now we can change the signs to pluses here. And now we have an equation where you can see that actually the difference between what we have on the left with what we have on the right is simply a rotation. So it's a rotation, and a rotation we can write a rotation in the following fashion. We have the vector I c dt prime dx prime, which is equal to a rotation matrix in 2 dimensions. So we can write that as the cosine of a certain angle alpha, cosine alpha minus sine alpha, sine alpha, and then here we have I c dt dx. So we simply rotate this vector to obtain this vector here. And if you choose a certain angle, I mean, this angle can be whatever angle you choose, you're going to satisfy this relation. It's a simple property of rotation matrices, basically. So if you have a vector, let's call this vector W, W prime actually, and we call this a matrix R, this would be W. W prime is equal to RW, and then here if you take the dot product between W prime with itself, this will be equal to W prime transpose W prime, and this would be equal to W transpose R transpose, which is the transpose of this, times R W transpose. And this means that R transpose R is equal to, I mean, this is equal to the identity because it's a rotation matrix, and therefore the dot product between W prime and W prime is equal to the dot product between W and W, which basically implies that this is true because this is actually the dot product between W prime and W prime, and this is the dot product between W and W, right? So we can write something like this, and from here we have two equations. I c dt prime is equal to the cosine of alpha I c dt minus the sine of alpha dx, and then we have dx prime equal to sine alpha I c dt plus cosine alpha dx. Now, for convenience, we can multiply this first equation by minus I, so I can get rid of the factor I, which will be equal to 1 here. Then we get 1 here as well, and then we get plus I in here. So these are the two equations that we will consider. Now we are going to choose an object that we want to describe from our two frames of reference, an object that is at rest with respect to the frame k prime with coordinates x prime and t prime, and it is moving with a velocity v with respect to the frame k. So basically it means that dx prime dt prime, which is the velocity in the frame k prime, is equal to 0. And the derivative of the position x with respect to t, this is equal to v. So from here we can say that, okay, for this object dx prime, which is 0 for the object, is equal to, of course, this object here, this part here, so we have sine alpha I c dt plus cosine alpha dx can be written as v dt from here. So we can solve this equation for the tangent of alpha, so we can divide by cosine alpha, so we get tangent alpha, which is equal to minus v divided by I c, or if you want we can write it as I v over c. So if we square the tangent of alpha, we have tangent squared alpha equal to minus v squared over c squared, and then we can add 1 on both sides, plus 1, 1 plus, But 1 plus the tangent squared of alpha is equal to 1 over the cosine squared of alpha. So from here we get that the cosine of alpha can be written as 1 over the square root. Actually, we have plus or minus 1 over the square root of 1 minus v squared over c squared. And then from here we can obtain the sine of alpha, which is simply plus or minus the square root of 1 minus cosine squared. So we have minus v squared over c squared divided by 1 minus v squared over c squared. And this is equal to plus or minus I v over c divided by the square root of 1 minus v squared over c squared, like this. And now we can substitute it. So this object here, 1 over the square root, we can call it beta, which is the Lorentz factor. It is the so-called Lorentz factor. So the cosine of alpha is plus or minus beta, whereas the sine of alpha is equal to plus or minus I v over c beta, for convenience. Now, if we go back to these equations for a generic object, we can write this as c dt prime equal to, now the cosine of alpha, we said that it's a plus or minus beta. So we have plus or minus beta, and then we have c dt, and then we have a I. So you can see that when we multiply sine alpha by I sine alpha, this is going to be a real quantity because we have I here as well. So we get another plus or minus because when we multiply this by I, we get minus 1. But we still have the uncertainty on the sign, so we can still write it as plus or minus v over c beta. So we get a real quantity. So let me close the bracket here. This beta with this plus or minus, we multiply this c dt, and the fact that I close the bracket is due to the fact that this plus or minus is not the same as the one for the sign. Here we have another plus or minus, but in general, if here we have a plus, we might have a minus here, because they are not related, if you think about it, if you think about the definition of the cosine and sine of alpha. But here, what do we have? We have v over c multiplied by beta, and also by dx. Then we have dx prime below equal to sine alpha times I, which is v over c beta with this plus or minus, and then we have c dt, and then we have plus or minus beta dx. We should make our choice of the signs here based upon the fact that this dt should have the same sign as this dt prime. It's quite straightforward to think about that, because if in one frame of reference time is moving forward, in the other frame of reference it must be the same. So here we have to choose plus. And of course we are forced to choose plus here as well, because if you think about it, these two here are paired because we had the cosine of alpha. So if we choose one sign here, we have to choose, of course, the same sign here. And it makes sense because here we can see that the sign before the space variable is the same. There's a plus there. Whereas, how can we choose this other sign? This one here or this one here? Now, if you think about a frame of reference in which the speed of light is much smaller than c, and we choose a frame, so the frame k prime is still with respect to the object, so x prime is equal to 0 in that frame. We must have the equation x equal to v times t in the other frame, assuming that the object is at the origin when t is equal to 0. So we must have this equation x equal to vt with the speed being constant. And from here, in order to get this, we must have beta equal to 1, and this is true if the speed of light is much smaller than c, so it's approximately equal to 1. And from here, actually, from the second equation, we have dx prime equal to 0, because the object is still with respect to the frame k prime, so we have 0 equal to v, so we have c divided by c, which is 1, v dt, and then we have this plus or minus, we still have to choose that, and then we have plus beta, which is 1 dx. So in order to get this, or if you want this, dx equal to v dt, we must choose a minus here. So we must have a minus. So here we must have a minus, and here we must have a minus as well. And now you can also rewrite these two equations properly, but they are indeed the so-called Lorentz transformations, which are fundamental in describing special relativity, and from them one can derive general relativity. One can extend the theory to general relativity to obtain a generic invariant length. This is actually very important because it's the first time in relativity that you encounter tensors, because ds is actually an invariant quantity, and with the language of tensors one can understand it in a better way, in a more precise way. If you think about it, what we did is actually an extension of rotations, because we have rotated a four-dimensional, well, in this case it's two-dimensional with the one-dimensional space and one dimension of time, but our space is three-dimensional. I mean, the dimensions of space that we know in the reality are three, and then we have one additional dimension of time. So we have, if you want, four dimensions, three dimensions of space and one dimension of time. And rotations can be extended to consider these additional dimensions